welcome to the lecture series of millimeter wave technology. So, roughly by millimeter wave we understand a section of electromagnetic spectrum of wavelength of dimension 10 millimeter to approximately 1 millimeter. So, it translates to a frequency scale 300 gigahertz to 30 gigahertz. But we also have some practical applications which are starting at 26.5 gigahertz. We have a band, and also we have some other applications at 24 gigahertz. So, for practical applications by millimeter wave, we understand from 24 gigahertz to 300 gigahertz approximately. So, now why do we need millimeter wave technology? So, for wireless communication already we have some popular applications like Bluetooth, Wi-Fi, wireless LAN. So, for Bluetooth, how much data rate it can support? So, maximum in kbps range. In Wi-Fi or wireless LAN, it can be increased to megabit per second or tens of megabit per second. But if we want gigabit per second, let us say through output. So, in that case we have only option that we have to increase the carrier frequency to millimeter wave. So, not only that, high resolution radar, so high resolution imaging, these are also possible by using millimeter wave frequency range. So, there are so many advantages at millimeter wave frequency range, then why do not we use millimeter wave frequencies? Why it is not so popular? So, obviously there are many problems and we have to solve these challenges, some of them already solved. So, in this class we are going to learn all these challenges, how to solve them, and slowly we will see starting from the source to receiver. So, what are the different components we use at millimeter wave frequencies? So, let us start with the band designation. So, if you look at the different band designation marked by this yellow color, so the Ka band, it starts from 26.5 gigahertz to 40 gigahertz. So, the whole millimeter wave spectrum, it is divided into several bands. So, among these some popular bands are Ka band, then the V band which is from 50 to 75 gigahertz, then the W band 75 to 110 gigahertz frequency range, and they are already in use for satellite applications, for radar applications, and now people are trying to use this band for wireless communications. So, if let us just look at a circuit, millimeter wave circuit. So, this is a millimeter wave circuit which is fabricated on a printed circuit board. You can see the black color dielectric material and the shiny is the copper. So, if I look at the left hand side, it has actually two parts, one high frequency component parts which is millimeter wave frequency component parts, and the right hand side, this is the low frequency component parts. So, it is its frequency range in microwave frequency or in RF frequency range. Now, for any wireless system we need antennas. So, this is an example of FMCW radar circuit. So, you can see these rectangular patches, these are actually the radiating antennas, and at millimeter wave frequencies the antenna dimension is very small. So, typically the resonating antennas, its length is lambda g by 2, that means half wavelength at the operating frequency. So, at 60 gigahertz for example, the wavelength is already 5 millimeter in free space, and then half of it, so it is 2.5 millimeter. And not only that, when we fabricate this antenna on some printed circuit board, so its dimension further reduces by a factor of root epsilon r, where epsilon r, this is called the dielectric constant of the substrate. So, at millimeter wave frequencies, antenna dimension, it becomes very small, just a few millimeter. So, as you can see in this circuit. So, this is actually an array of antennas 3 by 12 element. So, these antennas, then it is followed by low noise amplifier, then by mixer. So, mixer, it actually can down convert or up convert the carrier frequency. We can use non-linearity of any active element like a PN junction diode or a transistor to up convert and down convert the frequency. So, once millimeter wave frequency is down converted to microwave frequencies or RF frequencies, then the conventional RF components or microwave components can be used. So, this right hand side, it consists of those microwave components. So, this is a typical RF millimeter wave transmitter and receiver circuit. This is a conceptual diagram. So, in the transmitter circuit, you can see that we have a 60 gigahertz millimeter wave continuous source. So, which is being modulated by the baseband, it is coming from CMOS digital circuitry. So, the cost of any millimeter wave system, it depends on fabrication procedure. So, standard technologies in use are germanium, silicon and gallium arsenide material. So, in group 3, group 5 like gallium arsenide material, the circuit performance is better, but it is very expensive procedure. So, unless we can minimize the cost, it will not be applicable to consumer market. So, in CMOS or BiCMOS procedure, this cost is quite low, but unfortunately CMOS or BiCMOS process, it cannot be used for millimeter wave circuit design. So, in this particular example, then we can use that gallium arsenide or silicon germanium for the 60 gigahertz or millimeter wave generation, and the for baseband part we can use the CMOS digital circuitry. So, then after modulation and amplification, it can be transmitted by one antenna. At the receiver side, we have one receiving antenna, then the received signal, it can be 60 gigahertz, for example, this one 60 gigahertz pulse receiver, then it is demodulated by the CMOS digital circuitry. So, once it is demodulated and down converted, then we can use the conventional CMOS digital circuitry. So, what is the advantage of this system? The advantage is that this system can support multi-gigabit communication. So, that means this millimeter wave system for multi-gigabit communication without using any wiring. So, fiber optics, it can also support multi-gigabit communication, but in that case we have to use wiring for fiber optics. So, but millimeter wave communication, it has to face many challenges. So, one of them is atmospheric attenuation. So, this figure typically it shows the attenuation in dB per kilometer versus the wavelength. So, if you look at the diagram, we have a solid line and one dotted line. So, this dotted line, it corresponds to the measured attenuation in dB per kilometer at a 4 kilometer height from the sea surface, sea level, and the solid line, it corresponds to attenuation at sea level. So, if we measure attenuation at sea level, it is higher than that at higher atmosphere. Now, if I follow this curve, so from left hand side to right hand side, actually frequency increases. So, at 22 gigahertz, we have one attenuation band. This is due to the resonance of a water molecule H2O. Again, we have a 60 gigahertz peak here, where attenuation is very high. This is due to the absorption of oxygen. So, this is due to the resonance of oxygen molecule. So, again, if I further increase the frequency, we have one more absorption band at 118 gigahertz. This is again due to the oxygen molecule, and at 183 gigahertz, we have one more attenuation band, which is again due to water molecule. So, that means we have some propagation windows. So, if we want to communicate over long distance, we have to use these windows. So, otherwise, for example, if we use 60 gigahertz band for long distance communication, so signal will be highly attenuated. So, this attenuation, it depends on frequency as well as height from the sea level. So, as we see from this graph that at higher atmosphere this attenuation is much smaller compared to the sea level. So, not only that, fog, rain and sunstorm, dust storm, so all of these weather condition also affect millimeter wave propagation. So, this is a typical attenuation plot with rain rate with different frequency range. So, if you follow any one curve, so lower rain rate, for example 0.25 millimeter per hour to 1.25 millimeter per hour. So, for this range the attenuation is typically at millimeter wave frequency is 1 to 2 dB per kilometer, but for moderate rain, for example 5 to 25 millimeter per hour, it increases to 10 dB per kilometer, and for a cloud burst typically 150 millimeter to 250 millimeter per hour, this attenuation can increase to as high as 100 dB per kilometer. So, why this attenuation happens? Because the droplet, rain droplet, it scatters millimeter wave frequencies, and because it's the size of this rain droplet is comparable to millimeter wave wavelength. So, that is why this effect is more prominent at millimeter wave frequencies compared to the lower frequencies. For example, if I follow any curve, let us say for moderate rain rate 25 millimeter per hour. So, below X band the attenuation it is showing 2 dB per kilometer, but in millimeter wave frequency range typically it is increasing to 10 dB per kilometer. So, this is a problem for long distance communication. For example, is for a satellite link. So, for satellite it has to communicate between a ground based system to satellite, which is which can be as high as 36,000 kilometer above the earth's surface. So, we have to keep in mind when we are going to design any millimeter wave system, rain rate it can affect the channel performance. So, now long distance communication really possible at millimeter wave frequencies. So, we have actually one formula, we call it Freese law, by which we can calculate the free space path loss at different frequency range. So, free space path loss it can be given by 20 log base 10 4 pi r by lambda in decibel. So, where r is the free space distance, lambda is the wavelength. So, in this expression we are not considering any atmospheric effect, this is just due to the increasing distance between transmitter and receiver. So, why if this loss increases with distance? You can consider one transmitter, let us say it is placed at the origin of a polar coordinate system, and it is transmitting in all the direction. Now, I have an receiving antenna. So, the received power by my receiving antenna depends on the effective aperture of this receiving antenna. So, we can consider a spherical surface, so and the receiving antenna is placed on that surface. Now, the intensity on that spherical surface it obviously depends on the distance r. So, if I increase the distance from origin, then the power it decreases with r square. So, this loss we call the path loss, and it is given by this expression. So, it is a function of r as well as it is a function of lambda, the wavelength. So, here are some calculated values of free space path loss. For example, this first table showing the path loss value at r equal to 10 meter. So, at 2.4 gigahertz this typical path loss value is 60 dB, Now, if I increase the frequency to 60 gigahertz, where free space wavelength is 5 millimeter, so this path loss increased to 88 dB. So, not only that, if I keep on increasing the frequency, let us say at 300 gigahertz at sub-millimeter wave frequency range, so it further increases to 102 dB. So, now if I recalculate these values at r equal to 1 kilometer, so at 2.4 gigahertz we can see the previous path loss was 60 dB, now it is increased to 100 dB, and at 60 gigahertz from 88 dB it now increases to 128 dB. So, if you send 1 watt of power at 60 gigahertz, it will be attenuated by 128 dB at 1 kilometer. So, this calculation does not consider the attenuation due to atmosphere. This is just the free space path loss. So, this picture is showing a typical millimeter wave antenna, a parabolic reflector, and this is the feeder horn. So, now what are the advantages and disadvantages of millimeter wave communication? So, already we have seen that millimeter wave have high atmospheric attenuation. So, if we increase frequency, so attenuation will increase, and not only that, at millimeter wave frequencies we have some transmitting window. So, for any wireless link, so we have to use those windows to get minimum attenuation. Rain fade, that is another problem, and we have seen that attenuation it increases with rain rate. So, similarly it is also attenuated by fog, it is attenuated by sandstorm, dust storm. So, weather condition it affects millimeter wave propagation. Humidity, that also has an degrading effect on millimeter wave propagation. So, at 60 gigahertz we have seen that attenuation due to oxygen it is quite high, it can be 10 to 15 dB per kilometer. But if I go to that window, let us say 70 to 80 gigahertz frequency band, so in that band the attenuation due to oxygen it is very small, let us say 0.2 to 0.3 dB per kilometer. But a humid condition, let us say humidity is almost 100%, this attenuation can increase to 3 to 4 dB per kilometer just due to humidity. Then next is surface appear rougher, so diffused reflection increases. So, multipath propagation, that causes another problem. So, particularly from reflection from indoor walls and surfaces causes serious fading. So, this fading problem you might have experienced even at lower frequencies, for example, FM radio. So, you might have noticed that the radio when I place at one corner of the room it is working, but if I place at other corner of the room it is not working. So, this is due to fading. So, we have actually reflection of the signal from walls, from doors, from furnitures, and these reflected signals from the various sources they produces in constructive and destructive interference. So, which is will be a function of space. So, at some point then you will get some signal, at some point of this in the same room you may not get any signal. So, this is the, called the fading effect, and it is very prominent at millimeter wave frequencies. So, even just if you displace your receiver by a few centimeter, your signal level it may degrade. So, Doppler shift, another problem. So, Doppler shift as we know that it depends on the frequency as well as it increases with the velocity. So, but at millimeter wave frequencies the frequency is so high that even at pedestrian speed this shift can be significant. So, whenever we are going to use any portable device, we have to be very careful about this Doppler shift. So, it should be considered in our design. And another problem is shadowing problem. So, at lower frequencies, for example, 1.8 gigahertz or 2.4 gigahertz wireless LAN application. So, electromagnetic signal actually it can bend around our body. This is due to the effect of diffraction, but at millimeter wave frequencies the wavelength is so small that it can't bend around our body. So, what we see, what we observe at optical wavelength, shadow effect. So, similar effect we experience at millimeter wave frequencies. So, if I have a transmitter sitting just at back of me, so in front of me you can't get any signal. So, it is called the shadowing effect. Millimeter wave, it travels solely by line of sight and are blocked by building walls and attenuated by foliage. So, long distance communication it's in question. So, only line of sight communication may be possible. So, but it also has one advantage, that we can design densely packed communication networks, which is called WPAN system through frequency reuse. So, for example, let us say we are designing a wireless LAN like system in one building, which is using let us say 77 gigahertz frequency range, and we know that it will be highly attenuated outside the building. So, just in the next building we may not get any signal from that building. So, in that building then we can, in the second building we can use the same frequency spectrum for to design another wireless LAN like system. So, this is called frequency reuse, and highly dense network is feasible due to it. So, millimeter wave it shows optical propagation characteristics. So, that means it can be easily reflected or focused by small metal surfaces. So, even a few square feet of antenna is sufficient to generate pencil like beam, and it is diffracted by building edges. So, the wavelength at millimeter wave, as we have discussed, that it is 10 millimeter to 1 millimeter, and for resonating antennas which length is typically half wavelength. So, it is then 5 millimeter to 0.5 millimeter. So, that means the antenna size it decreases. So, we can design arrays of antennas at millimeter wave frequencies easily, because antenna size is small. So, an array of antenna we can easily fit over let us say a square feet area. So, potential applications: very high resolution radar, communication link typically more than 10 gigabit per second. So, before starting the next part, let me discuss about Sir J.C. Bose's work. So, you will be surprised to know that the first millimeter wave system were built by Professor J.C. Bose in Kolkata in West Bengal. So, in 1895 actually he demonstrated a millimeter wave system, and it is typically working at 60 gigahertz frequency band, and he communicated over a distance of 23 meters. So, at that time these different sources of millimeter wave frequencies, how to transmit it, how to receive it, how to design different components, so all of these were not known that time. So, he had to design all of these components, starting from the transmitter, how to receive it, and then he had shown the reflection property, refraction property, and the polarization of millimeter wave, and also he has shown that millimeter wave it is nothing but another form of electromagnetic wave which follows more or less optical properties. So, in his experiment, typical wavelength he used starting from 2.5 centimeter to 5 millimeter. So, roughly it corresponds to 12 gigahertz to as high as 60 gigahertz. So, this is an replica of the original system designed by Professor J.C. Bose in Kolkata. So, you can see this is a box. So, inside the box we have a millimeter wave source which is nothing but a spark gap, and then he used a tube, metallic hollow tube, as the transmitter. Now we know that it behaves as an antenna, and we have a turntable here. So, where he can use the prism and other structure to show the refraction and reflection property, and on the right side we have a receiver. So, this receiver receives millimeter wave signal. Then how to sense this millimeter wave signal? So, he designed one detector which is a metal semiconductor junction. I am going to show the picture in next slide. So, when millimeter wave signal falls on this detector, it provides DC current, simply DC voltage. So, we can then detect this DC voltage by using a galvanometer. So, in this slide you can see the different components used by Professor J.C. Bose. This bottom right corner, it shows the spark gap. So, we have two gaps between these two pins. High voltage is applied between these two pins, which generates sparks. So, sparks, it contains a wide electromagnetic spectrum starting from optical wave to RF. He used the millimeter wave frequency range. So, he placed this spark gap inside this box, and then you can see the transmitting part here. So, inside we have the spark gap. So, from which electromagnetic wave is being transmitted by this pipe. Now we call it horn antenna. So, this is a prism made of a dielectric material. So, to show the refraction property of electromagnetic signal, and this is the receiver side. So, at the receiver you can see top right figure. So, we have a point contact detector. So, this is it. It is made of a metal needle, and the bottom side, it is a semiconductor material. It is galena, lead sulphide. So, it has nonlinear characteristics, so almost similar to a PN junction, and when electromagnetic signal falls on this, it provides DC voltage. So, then by measuring this DC voltage, we can detect electromagnetic signal. So, he invented this type of detector, so long time back in 1895. These are some polarizers. So, this middle part you can see some parallel metallic wires. So, when electromagnetic signal falls on it, so if the electric field is perpendicular to this metallic wire, it can't pass through this wire mesh, but if the electric field is parallel to this wire, then a fraction of the component incident electromagnetic wave, it will pass through this wire mesh. So, similarly, he designed some other polarizers. So, it is nothing but a book. He used several metallic plates inside the books. So, these plates are parallel to each other, then any electromagnetic wave whose electric field is parallel to this metal, it can pass through this book. He also designed another polarizer. This is made of jute, and inside he used different wires. So, we see that even at in 1895, long time back, J.C. Bose in Kolkata designed the world's first millimeter wave system. So, after Professor J.C. Bose's work, almost 50 to 60 years, there was no work at millimeter wave frequencies. So, again it started during Second World War, 1940s. So, now we will take a short break, then again we will start.